screen. Okay. So I think this was the question that I've told you about. So in this particular PDA, there are many problems here. First of all, we are not reading anything here. So we are only reading A and B in this one. We are not reading C here. In this particular instance, we are reading all the things. Okay, so that is uneven here. Either we read all the A, B, and C because I have to read all the A, B, and C, but just I have to perform the operations in such a way that it shows that I have read or not read. Okay, so I again build the answer is particularly same for this one. So I just again build what exactly the exact automata will be. So I think I just quickly I just made the automata. So there are many thing wrongs here. So the question was that the number of A's should be equal to the number of B's, or the number of B's should be equal to the number of C's. Okay, so there is a or here. So I think this you consider this one as a union. So what I'll do first, I will draw this and then I will draw this. Okay, so now you know that the input here will be A, B, and C. So that is confirmed here. So A, B, and C will be your input alphabet. Now, what you do, you take the number of A's. Okay, so first of all, the cases will be same. It will be either greater than one or it will be less than one. Okay, so first of all, I just uh, take this A and put it on the stack. Okay, so take this A, put it on the stack, that A Z not, and then there is a at the top of the stack. There is a, you push the number of A's. Okay, so all the A's are now on the top of the stack. Now I want to start popping. Okay, so there are two major cases if you remember. So I do not want to discuss now. I just want to pop it. Okay, so top of the stack, the B is coming at the top of the stack. There will be I, and you start popping and you keep continuing. Okay, so it will be a B at the top coming, A at the top of the stack. That is okay. So now by doing this, there will be two scenarios here. The first scenario can be that the number of A greater than the number of B's. Yes, or the number of A's are less than the number of B's. Okay, so that will be a two scenario. So the first scenario, what will happen when you pop? So I push the number of A's. When I start popping, there will be a on the stack. In the second scenario, okay, so that is problem. The number of A's are less than number of B's. So in the second scenario, there will be a and your pointer will be at here and the stack will be empty at Z0. Okay, so how to approach this one at this particular state? If I say the state as a Q1, okay, so now there can two scenarios occur. First, you can, if you want to do it, you can do it here, but I am changing the state here. So first scenario will be you are here. So I'm talking about this scenario. So in this scenario, your input is B, your input is B, and at the top of the stack, there is a Z naught. Okay, input is B and there is a Z naught at the top of the stack. You do nothing. Okay, so don't do anything. If it is happening, it is moving to the state Q2. I'm calling it a Q2 state. And the second scenario will be that nothing is input because all the thing is over. So the pointer is standing at here. So nothing is input, and at the top of the stack there will be a, and you do nothing. Okay, so the top of the stack there is a, so the A will remain as it is. Okay, so now I also have to see the number of C's also. So I have to define what happened when I see a number of C's. Okay, so if this is exactly the input will be like this, the C will also be there. Okay, so by seeing the number of C's, there is no need to do anything. Okay, so I also have to define this step. However, we are not putting it onto the stack, but I have to define this step. Okay, so in the previous one, I am not defining this step. Okay, so for this one, either the C will be, the C can come after here, or the C can come after here. So in both, define both of the cases. If C is coming, your main concern is you do not put anything at the top of the stack. Okay, so just wait a second. Okay, sorry for that. And now it can be either after the pointer here, I'm again standing here, and now okay, so now I have to change this step particularly. Okay, so now if you're also think that there is a C here, when there is a C, you do nothing because C will also be there. We have to define the step, however we are not putting anything. Okay, so now in this particular scenario, if you are seeing at Q1, when I'm talking about when the number of A's are greater than the number of B's. Okay, so in this particular scenario, what will happen, at the top of the stack there will be one A and two A's will be popped. Okay, so now this is defined here, but after the pointer will move to the right, there will be a C. There will always be a C, because if I consider that the if it is, if I consider this question as A plus B plus, okay, so now in this particular question C will always be there, so I can consider that if C is the input, if C is the input and at the top of the stack there is a, so you do nothing, so just remain the A at the top of the stack. Then again there are a number of C's that can be coming. Okay, so if there are number of C's are coming and at the top of the stack there can be either A or the stack will be empty. So do nothing if at the top of the stack there is I, so just remain the I as it is, as well as if at the top of the stack there is a Z node, so don't do anything. Okay, so now this just move it to the final state. It can be written like this one, epsilon then Z and then Z naught, and it is moving towards the final state. Okay, so I think that that will be PDA for when the number of A's are not equal to the number of B's. Sorry, the number of A's are not equal to the number of B's. Now I have to define the automata where the number of B's are not equal to the number of C's. Okay, so in this particular instance, what can I do? So suppose I draw, I just taken these both things individually. So now I'll taken this one as q3 and this will be your q4. Okay, so for q4, the first thing, because I have to check num b's are not equal to the number of c's, so for that I do not need to care about a, but a will be in the language. Okay, because the input is a plus a, b and c, so a will be in the language. For that I have to consider this thing also. So a, now a is coming. So when there is a, you don't put a onto the stack. Okay, so what you can do, so you can consider z naught. So z naught will remain at the top of the stack. So I'm not doing anything. So this can be okay. So now another thing can be, now when there are B coming, so when there is a B coming, so what I'll do, I'll there is a Z node at the top of the stack. I'll push that B and I'm keep pushing. I keep pushing. So it will be B at the top of the stack. There is a B and you keep pushing B. Okay. So now I have to check that the number of B's are equal to the number of C's. So there are two cases: B can be greater than B and B can be less than C. Okay, so thus cases are same here. Okay, so now I'll take this case B, B and B, and then there are two C's, and then there is a B, 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 and just there are greater than C. Okay, so there are two B's and three C's. Okay, so take the cases and there will be a B, 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 and for the two C's I'll pop this, and it will be a Z not at the top of the stack in this case, and for this one I'll push BB and the pointer will be at C, and at the top of the stack this is an empty stack. Okay, so at the top of the stack there will be a Z node. Okay, so both of these can occur, both of these things can occur. So I can say that when my input is C, so I'll say when I'm talking about this one, when my input is C, when my input is C and at the top of the stack there is a Z node, and at the top of the stack there is a Z node, suppose. Okay, sorry about that. Because by doing this, I think I'm not popping anything, so I have to start popping also. So I'll change the state. Okay, so now when the C is coming and at the top of the stack there is B, just start popping. Okay, C is coming at the top of the stack, there is a B, you start popping. Okay, so now in this case either you will get a Z node or you will get a Z node or you will get a B at the top of the stack. There are two cases. Okay, so for this case, for this particular case, I am now your pointer is at a C it means that it is not equal, the a and b and c's are not equal, so you can move it to the final state. So I'll see at I am when the input is c, when the input is c, and at the top of the stack there is a z node, so you do nothing, so z node will remain as it is, and I'm moving towards the final state. In the similar way for this another one, what is the another one here? Yeah, that your input is over, your input is over, and you at the top of the stack there is a b. Okay, so for this one also you can move to the final state. You can say that when the input is nothing and the top of the stack there is a b, you do nothing, so b will remain as it is and you move to the final state. Okay, so this particular question denotes that the number of b's are not equal to number of c's. This particular question below denotes that the number of a's are not equal to the number of b's. Okay,
Sir,
so yes, yes.
sir, in NA not equal to NB1 in the Q2 state,
Mm-hmm.
I think there would be one more thing defined as B comma Z naught slash Z naught.
B comma Z naught slash Z naught. So it on the loop.
Yes, sir.
Okay, so just can you tell me the scenario when will it occur?
So
Uh,
A B B B B C.
A B B B B C. Yeah, this one.
Yes, sir.
Okay, so just let me confirm. So A, and then I think you will pop it. Okay, so now there will be. Okay, so there are number of B's. Okay, so I have to check that the number of B's are not equal to the number of C's. So that will again happen, that is correct. Okay, so in that case I also have, there will be a z naught at the top of the stack and the number of b's are coming. So what I'll do nothing, by seeing the number of the stack will remain as it is. I think it will also happen in this case. I don't think I have considered more than one, so just let me check. uh, uh, bb just check this case also. I think it will also happen in this one because we have not taken care in this one. It can happen because the a's are not dependent upon the b, but the if there are b's, something like this. Okay, so I don't just let me confirm. So a we do not push, we will not push it on the stack, and then there will be a b, I will pop it, and then there is a c coming, and at the top of the stack there is a, I don't think there is that is completely defined here. Okay, so if I think that is the correct one, but if you think, just take another two or three scenarios and just test it, and it is still not complete because if you're seeing this is a totally different PDA and this is a totally different PDA. Okay, so now our main concern is this a union. Now I have to combine these two automatas. Okay, so how can I combine here? So if you remember that I've told you the advantages of a null production in NFA, that it is very specific in combining or taking a union of two different DFAs or NFAs. But uh, now how can you combine this one? So first of all, in both the cases, if you're seeing in both the cases, a will always come. Okay, so a will always come. So one case, if you're seeing a and z naught, here there is also a and z naught. Okay, so I think you can combine these two states into one. Okay, so how can you combine this one? So I'll say that a z node, and I'll, in this particular I will push a onto the stack. In this particular this particular question, a z node, I will do nothing. Okay, so I will do nothing. Now if you're seeing that a z node, now z node is pushed onto this stack, so this particular production is not needed here. Okay, so because in the first time, if z node is empty, only a will come one time, so you can push it. So when the it is already pushed, so q naught, there is nothing, there is, this production is not needed here. Okay, so now when the number of a's are equal, not equal to the number of b's, you can go towards this particular automata that I can say that as pda1 by starting from this q, what I'll say, initial state, q initial, and you can go to pda2 when you want to check when the number of b's are not equal to the number of c's. Okay, so now if you're seeing here on the same input, and on the same stack symbol. If you're seeing same input and on the same stack symbol, they are going to do two different states, that is your q node and a q4. So I can call this as a n non-deterministic push down automata. So that is why in this particular question you can draw a NDPDA. That is why it's called NCFL. But you will not be able, if there is a and here, so it becomes a totally different question. Now it becomes that n number of a should not be equal to number of b's, as well as number of b's should not be equal to number of c's. Okay, so that becomes, because if you're saying the dependency becomes here two way. First way will be that you have to check the number of a's not equal to number of b's. So a second dependency will become the number of b's should not be equal to number of c's. So that will never be a CFL or a NCFL. It is not possible. You can also try it. You will never find any push down automata that can be made for this particular question. Okay, so this is the, I think that is the perfect solution. But if you find anything else, you just try a different combinations. But I just want to make you see that there are also these questions that when there is number of a's not equal to number of b's, so how to deal with this question? Because mostly you will see this question that number of a's is equal to number of b's. So to how to deal with this? Okay, so that will be your solution to this one. And when there is a and, keep in mind there are all the threes are no, because the dependency become two ways. Okay, so at in a stack at a particular amount of time, you only have to do a one single comparison. If you are not if this particular thing is demanding two comparisons, like that the number, when you are pushing a stack here, this is demanding two comparison, that the it should not be equal to the number of b's, as well as it is not equal to the number of c's. So in a stack you cannot check that. Only you can check two terminals at a time, but you cannot check three terminals at a time. So that is the problem. Okay, so now I think we have done our Turing machine. So Turing machine. Okay, so there is other thing called Turing church thesis. Okay, so I'll tell you in informal language, but there is also a formal definition. Don't worry about it. In a PPT I will tell you about it. But before telling you about the Turing church thesis, just understand what exactly this statement represents. Okay, so it is still now. Okay, just wait a second. If you have, just wait a second. Just a bit. So there is no quiz in this class. Okay, so only one quiz, that is at 6 p.m. Okay, so just be sure to attend it. Don't worry that there is no quiz in this particular class. Okay, so now the Turing church thesis, I will tell you informally what exactly it means here. It exactly means that it is saying that whatever the problem. Now this is a very important statement. I can call this a statement, because with the help of this statement we are able to tell we are this statement becomes so popular that we are now calling your modern computers as Turing machines. Okay? So exactly the theoretical concept between modern computers and Turing machine is the same, but this problem made this particular statement made it so popular that we start calling a modern computer a Turing machine. So why? What exactly was the statement? It just in the statement they said the Church is a different scientist and Turing is a different scientist. So Church devised another calculus called a lambda calculus. Okay, so I'll tell you about it. Don't worry about it. So just it is a informal information. So lambda calculus. Now, what does Alan Turing did he devised a theoretical machine? Okay, so that theoretical machine is called your Turing machine. So that Turing machine is can take this lambda calculus to solve any. Okay, so now the statement goes like this, that any problem that is solved by a modern computer, so it is in an informal way, but the meaning of this that in the formal notation it's a little bit difficult, but if you understand it completely the formal notation, but the meaning of this is the statement that I'm saying, that any problem that is solved by a modern computer, that any problem that is solved by a modern computer can also be solved by a Turing machine. Okay, so this statement, first of all, there is no proof for this statement. There is no proof that this statement is true or not. So till now there is no proof. So this is again one of the open problems in computer sciences. There are another problems like NP and P problems are also open, that NP is equal to P, something like that. So this problem is also open till date, and this problem is also open that you have to prove that your modern computer is equal to the Turing machine. Okay, so every problem that is solved by your modern computer is solved by a Turing machine, and many scientists give many problems that is solved by a modern computer, but the equivalent Turing machine for that same problem also exists till now. Okay, so the till now no scientist has been able to find any problem that is solved by a modern computer but that is not solved by a Turing machine, so till now. Okay, so you can also try to solve this problem. This is a still open problem in computer sciences, and I think there is a Turing Award like a Nobel Prize for computer scientists, and in that also some people try to solve this one, but there is no actual proof for this one. So there, because there are many problems. So first, if you are able to solve this problem that particular NP is equal to a polynomial problem, only then I think my this is my point of view, only then think you I think you can answer this, that a particular problem that is solved by a modern computer can be or cannot be solved by a Turing machine. But these are two very popular open problems right now in computer sciences. You can also try to solve it. Okay, so now I will get back to this one with a formal notation, but you understand this, that the actual meaning of the statement is this, that any problem that is solved by a modern computer will also be solved by a Turing machine. So till now there is no problem, there is no problem exist that is solved by a modern computer and not solved by a Turing machine. Okay, so now it is now you will also be thinking that how it is possible. There are many problems that can be solved by a modern computer, but there may or may not be many complex problems. But that this Turing machine actually, this we are just studying the introduction of Turing machine, but it is a much more complex than just a basic if you're seeing the state and state transition diagram. Okay, so every Turing machine can also be represented in a particular binary number. Okay, so that is another way to represent. So there are many Turing machines. Okay, so I can say there are infinite Turing machines. So one Turing machine will always be there to find a solution of a particular problem. So that is for another day. So that is a very advanced concept, that how to represent it in binary every machine. So don't worry about that. That is not your part of the syllabus. Okay, so now I think we are doing some questions here. So if you understand the questions that we have done in the previous class. Okay, so I have given you the question, that is your third question, that because I said that how this Turing machine act as a transducer. Okay, so I think in the tutorial or in the class when we are doing a Mealy or a Murray machine, so the property of a Mealy and Murray machine, that they can act as a transducer. Okay, so why they are acting as a transducer? What is exactly a transducer? When you convert one form of input to another. Okay, so one form of input to another. So another can be anything. So mostly these are electrical impulses, these inputs are. So if this is there is a zero, it means there is no voltage. If there is a one, there is a voltage. So in context of transducer, we would do the 0 and 1 in this way. But I already told you that this if a million Murray machine is a subset of the Turing machine. Okay, so this is your finite automata. So this is your Turing machine. So if you are able to draw a transducer in million Murray machine, you will also be able to draw a transducer in a Turing machine. Now it is very easy in this one, because if you see that you can read as well as right. Okay, so that is a very good feature, that you see for one's complement you can see a one, and you and you convert it into a zero. Okay, so you can write it on the tape. Okay, so try to do this question, take like 5 minutes and try to do this question. Just take one input, something like uh, 10101101. Okay, so just take a big input and try to again draw the diagram for this. Okay, so if anybody has done it, just share your screenshot, so I can also tell you that if there is anything wrong in that. Or okay, so try this question, like take like 5 minutes, I will tell you the solution. Okay, take it, do it. Okay, I'll give you a hint in this one also. There is no need to go to the final state. Okay, so you can, there is also possibility that there is no final state in a Turing machine. That is fine. Okay, so you do this. Okay, so it's a very easy one if you remember. So you only have to take, suppose if you want to take a small input, so you can also take a small input here also. So it can be 1100. Okay, so suppose that you are standing at here, so your pointer is at here. I will always assume my pointer is here, so don't worry about it. This is your default setting, that whenever you are taking the input, you will always assume that your pointer is on the input. Okay, so now you will at the state q node. Now what you will do, if you remember the transition symbol, I write it, so it will be a q, and there is something called a x here. So x is your tape symbol, so everything that you are putting on the tape is your x. And then you can move to another state, you can take another blank symbol, and you can change to it, either you can write or read here, and then you can move it to. Okay, so there is again lot of x's, so just let me change the notation a little bit. So this is your x, this is your x, and it will be your it can either be your left or right. Okay, keep in mind it can either be left or right. So there are many Turing machines, so I'm only talking about a simple Turing machine that contains this transition symbol. Okay, so in other Turing machines, there you will see the transition symbol can vary, so left right, or they will say that it just stay there, so that is left right, and it is denoted by a hash. But don't get into it right now. I will tell you about all the various Turing machine that exist there. Okay, so I'm starting with the one. So one is my input. So what I'll do, I convert into 0 and start moving right. So every one, if there is any one, so I'll start moving, convert it to 0. I'll convert it to 0 and start moving right. Here I again find a 1, convert it to 0, start moving right. Okay, so now another can be at the starting state, you can also get a 0. So if there is a 0, you convert into 1, you convert it into 1, and you keep moving right. Okay, so now you will your pointer, when the one you have converted 1 to 0, and your pointer will be staying at here. Now you got a 0, you convert it into 1 and keep moving right, you convert it into 1 and keep moving right, and you will find your blank. Okay, so uh, either you, if you want to do here, you can stop, there is no need to go anywhere. But you can also you can also move this pointer towards the starting of the symbol. Okay, so it can be moved like when there is a b, there is a blank symbol, and you do nothing, just keep the blank as it is and keep moving left. Okay, so in the path you will get a number of zeros, you don't do anything, keep moving left, you get a number of ones, you don't do anything, keep moving left, and in the end you will keep moving and you will find a blank here. Okay, so you will get a blank here. When you got a blank here when you got a blank here, so don't do anything, move towards the right of the pointer. Okay, stop here. Okay, so if you want to draw till here, that is fine, there is no problem in that. For just, it's just a courtesy, it is just a courtesy, everything that I'm doing, it is just for the sake of courtesy, that I move my pointer to the starting notation. Okay, so it is just a courtesy that that wherever your pointer was started, you can again lead it back to it. Okay, so that is just a common courtesy that in every book you will find it. But if you want to stop here, there is no problem, so you can just stop here. I think uh, it can be, I think it is fine. Okay, so either it's a 0, you move it to 1, either it's a 1, you keep it 0, and then keep moving right. Then you will find a blank, and either you will move a left or right, or you can go to the final state if you want to. If you want to move to the final state, you can also write a final state here. Here you can also consider a final state if you want. Okay, so there is no problem if there is no final state in the Turing machine, because most of the time in most of the questions, if you see that there will particularly there will not be a final state in many questions. Okay, so because we are doing because Turing machine is acting as a transducer here, so in transducer most of the time there will in the state transition diagram there will not be a final state. So that is why I'm not taking a final state. Okay. So now the second question can be try to build a Turing machine for 2's complement. Okay. So try this. I think that was a very easy one. I think you can easily do this one. Okay. So just think about this one, that something like this input is here, your pointer will be always there. Now you have to move to the right, extreme right, and you start from here. Okay. So if you remember how to take a two's complement, so when there is zero, keep the zeros as it is. When there is a first one right as it is. After that there will be all the complement, take the complement. Okay. So try to do this one. The problems the assumption was same here. Okay. So the assumption that we find that was same, that was done in Moore is in Millie machine. Okay. So try to do this question. I think it's a very easy one. Okay. Try it.
So,
Yes. Yes.
so in the above question,
Mm-hmm.
so can't we just leave this final state at the second state that you wrote, like
Yes. Yes. You
BBL?
can. Yes, yes, that is absolutely fine. If you want to make it a final state and you just don't want to do anything, this one also you can forget about it. So that is fine. There is no problem in that. Okay. So it's just a common courtesy when you converted it, your pointer will, I think, will be at blank. So you can accept it here, but it's just a common courtesy to move the pointer towards the start of it. So that is why I've conducted these extra steps. Okay.
Okay.
Okay, so how to do this one? It's again, I will follow the common courtesy that will I will take my pointer to the starting of it. I think Varun has given the answer. Okay, Adarsh has also given the answer. Just let me confirm. Okay, it seems correct. Uh, Okay, so just keep in mind that we there are two things, okay, in this one, that most of you will be thinking that the final state is a necessity in Turing machine. So I'll again tell you that there is no need to always contain a final state in a Turing machine. Okay, so there is something called a halting. So actual meaning of halting is stopping. Okay, so whenever you just stop, your Turing machine will stop at a particular instant by just taking a look at the diagram. Okay, so if you see this particular diagram, at state q2 there is no loop. Okay, so if you are seeing after particular loop that you will convert 1 0 to 1 1 to 0, you will land at q2, and your q2 will just take your pointer to this one, and in this q2 there is nothing defined. Okay, so this thing is called your halting, that your Turing machine just stopped. Okay, so also you can accept anything by following the principle of halting. There is no need of the final state. Okay, so if you are following halting, there is no need of the following the final state. Okay, so, but if you want to stop it by a final state, that is also fine. But in those context or in those questions when your Turing machine are acting as a transducer or a copier or a adder, binary BCD adder, most of the cases you will find the general diagram, they will not contain any final state. Okay, so just keep in mind that if, try to avoid using these final state in these kind of questions. Okay, so you can do any questions by using a two way by just halt. Okay, so halt means that it will when it reach at q2, there is nothing to do here. Okay, so I'll again show you here in this one what is the halting principle. So always the decidability and undecidability, I will tell you about it later. The decidability and undecidability will also depend upon the halting of the Turing machine. Okay, so if your Turing machine halt means stop, it means that it's a decidable problem. But if your Turing machine does not halt, it is just keep working and you cannot tell when will it halt, then it becomes your undecidable. But don't worry about it, I will talk about it later. But just see now, if you remember, this is your blank and this is your blank, your starting pointer will be here. Okay, so I'll do nothing here at the starting point. Okay, so there is a q node, and at a q node you will keep moving right. Okay, so when there is a one, there is a one, keep the one as it is and keep moving right. There is a zero and there is a zero, or keep the zero as it is and keep moving right. Okay, so you have to keep moving right until you find a blank. Okay, so you will reach here and you will find a blank, and then what you'll do from blank, you don't do anything, keep the blank as it is, and you move to the left. Okay, so now my pointer is at here. Okay, so now for this one, this is very simple. Now for this one it's very simple. Now for q1, if there is a zero, keep the zero as it is, do not do anything, and keep moving left. Okay, so when there is a first one, when there is a first one, if there is a zero, don't do anything. When there is a first one, keep the first one as it is. So that is why I'm writing it on an arrow. When there is a first one, keep the first one as it is and keep moving left. Okay, so now here everything will be changed. Okay, so now this is your ones complement. Now where there is a zero, move it, keep it to one and move it to left. When there is a one, keep it to zero, move it to left. Okay, so I think your pointer will automatically reach a blank here. So when you are reaching a blank, so when you are reaching a blank here, keep the blank as it is and just move the pointer towards the right for the courtesy. Okay, so move the pointer towards the right for the courtesy. That will be your q3, and that will be, so this particular state signifies that your Turing machine halted. Okay, so it means it stopped. So there is no need to draw a final state here. So try avoiding avoid the use of a uh, final state in these particular questions. Okay, so again, this is again I'm telling you that this step is a courtesy. This particular step is a courtesy, because if you are at here at the blank state, you can again say that your everything is changed. Okay, so because at the state q2 you will find that your two's complement is completed. Okay, so at the state q2 you will find that your two's complement is completed, but it is not halting anywhere, because there is always a q2, there is a loop here. So that is why I've changed this state. So just take this state to q3. Now this q3 signifies your halting. Okay, so just wait for a second. Okay, so again, if try avoiding using a final state, because I do not know exactly the reason that why I am not using a final state here. So I will tell you about this final state in the next lecture. Okay, hold for this final state for the next lecture. But I will again tell you exact reason why final state was not included, or you can or cannot include. So I am not specifically, or I do not specifically know about this concept. Okay, so I'll tell you about it in the next lecture. Just
Sir,
wait for a second. Yes, yes.
sir, is it possible for us to get the two's complement in the long way, like taking one's complement and adding one to it to get the two's? Can we implement that using Turing?
Okay, so yes, you can implement that. I can also show Turing machine as a adder. Okay, so if the adder is possible, so you can do this. Yeah, you can do this by using a long way. You can
Okay,
also.
sir.
Okay, so I'll do this question. So when Turing machine is acting as a adder, so in this one, what you want to do that suppose this x is a variable, and in this x there are three ones are given here. Okay, so what can you do? So you have to count the number of ones here. Okay, so here it is 3. So if there are 4, so here it will be 4. Okay, so now suppose there is input like this one, that blank blank, and then there is a 1 1 1, and there is a 0, and then there is a 1 1 1 1, something like this. Okay, so then again there is a 0. Okay, so it is separated by a 0. If you're seeing, it is separated by a 0. So what I want that I want to separate this particular 0. I just want to completely eliminate it, and the answer should be like this. Okay, so 1 1 1, this 4 can be combined 1 1 1 1 together. So the on the tape it should be like this. Okay, so that will be your next problem that I will discuss. So I will tell you about Turing machine can act as a adder, as well as Turing machine can act as a comparator. Okay, so I will also tell you about, I will build a machine, or I will put that particular question in a tute. So comparator means that you have to compare the number of ones. Okay, so here we have deleted this one. So here it can be like in this 0, this. Okay, so I consider this as a and I consider this as a b. In this particular question, if you are seeing, the number of a's are greater than number of b's. Okay, so comparator, there are three things for comparator: a equal to b, or a less than b. Okay, so I will explain the problem, and I also draw the Turing machine for a comparator. So Turing machine has various different purposes. Okay, so Turing machine can act as a copier also. So if you want to copy a particular input to the tape, that it can also act it as. Okay, so for these three questions, I will include in either a tute. This is a very important concept of this, either a tute, or I'll try to cover this in the lecture. Okay, so now there is one concept that is remaining. So just let me show you the syllabus as the time is over. So just let me show you the syllabus, that which part is remaining and which part is covered. So I think we have enough time that we can cover all the syllabus almost. All the things are covered, right? Okay, so if you look at your first course learning objective, that says that you the comprehend regular languages, finite automata, and develop ability to provide equivalence between regular expression, NFA and DFAs. I think we have covered our first course learning objective pretty efficiently, and most of you, because we have devoted many of the time towards this finite automata. Okay, so all the things in the first course learning objective is already covered, and the second one, I think this one is also, we have done it very extensively. Push down automata, we have done like 20 questions for push down automata, 10 in the tut, and 8 in the tut, I think 12 to 10 in the lecture also. And the context free language, there is only one thing remaining in this one, that is your ambiguity. Okay, so I have taken a question in the tube to explain what exactly is ambiguity, but don't worry about it. In the next lecture I will also tell you about it with the proper definition. Okay, so I have proper definition, but I'll give you a proper example for this one. And the last course learning objective is to apply the concept of recursive and recursively enumerable language and design efficient Turing machine. So we are standing at here, so I will tell you about this particular concept. Okay, so recursive, what is recursive and what is recursive enumerable. So I will talk about it the next week. So I think most of our syllabus will get completed by then. So only thing that I have given it to you for I think for your assignment. So okay, so for assignment also there is a news. I'll extend the deadline of the assignment to 25. Okay, so I've talked with other teachers also. So I will extend the deadline for your assignment for 25. Okay, so now only this one is remaining, pumping lemma for context free grammar. That particular topic is your self study topic. Okay, so we have to give I think some topics to you for your self study. So pumping lemma for context free is again similar to pumping lemma for a finite language. You just have to read the definition. I think you can easily identify that but a particular language is context free, or whether a language is not context free. So we have done enough questions, and also I think a file that is containing like 50, I think 100 questions of these particular things asking about regular context free is already uploaded in this week. Okay, so in this week you will find all the questions. Okay, so make sure that you take that file into consideration also. And these two topics I have already given to you for your assignment. Okay, so these two topics, and then this is your Turing machine. So this is some part of it is remaining, so I will cover all the thing in the next week. So make sure that you attempt all the lectures in the next week, because Turing machine is it's a very simple concept, but most of the people find it very difficult. Okay, so it is very simple concept. If you're seeing how to design a machines, it's very easy to design. Most of the people also got confused in devising the machine here. So there is only one doubt remaining, that is why I'm not taking a final state here. That will I tell you in the next lecture. And that there is another thing that I've completely forgotten about, that is your ambiguity. Okay, so that also I will talk in the next lecture. Almost all our course learning objective as well as our syllabus is completed completely. All Although I also given you some extra topic that is not a part of the syllabus, but that is just for your complete understanding of this course. Okay, so okay, so you can move on to the next lecture, and just remember to